Now looking at meanings of different terms. Velocity, well, what's the meaning of velocity? The rate at which position changes. And we all should know by now, hopefully, what that means. The basic example that we're going to use is that position, well, an example where position changes by 20 meters in 4 seconds, we get an average velocity of 5 meters per second. This is, of course, the example we used when we talked about units. And, of course, the units of velocity are delta S over delta T, which are units of meters per second. This seems pretty redundant with what we did before, and if it does, that's good. That means you have a pretty good understanding of velocity. When we look at meanings, we're looking at the term. When we look at units, we're looking at the units and trying to get the term. So we're looking at it from two different perspectives, and hopefully the two perspectives will give us something like binocular vision, where we can see things more clearly. Meaning of acceleration. Acceleration is the rate at which velocity changes, as we have again said before. An example, if a car velocity goes from 5 to 20 meters per second in 3 seconds, then we have a velocity change of 15 meters per second distributed over that 3 seconds, so that on the average we have 15 meters per second divided by 3 seconds, or 5 meters per second squared of acceleration. That means 5 meters per second of velocity change per second of time. And the units are the units of delta V over delta T, meters per second over seconds, which we write with a little algebraic rearrangement as meters per second squared. Now, getting into some more subtle meanings, what is the meaning of force? Well, we could define force, or the idea of force, in terms of what force does. What does force do? It can do two things, and it does a combination of two things whenever it acts on an object. The first, and perhaps most obvious for a lot of objects, especially for solid objects, is that force tends to accelerate objects. If we have a net force on the object, that is, if the applied force is greater than the forces resisting motion, then the force will accelerate whatever object it's acting on. And or it can deform objects. Okay? Now, acceleration, a force can accelerate things by rotating it or by translating it through space. Here we're just going to talk about translational acceleration, although we do understand that forces do give rise to torques, and we think of torques as the source of angular acceleration or rotational acceleration. Really, it's the forces, but we translate force into the torque for that situation. However, if we're talking about translational acceleration, the acceleration of the center of mass of an object, then we would say, for example, that a 5 kilogram mass, when accelerating at 10 meters per second squared, will require a net force of 50 newtons, using Newton's second law in a very familiar way. The units, of course, are units of mass times acceleration. We've multiplied mass by acceleration here. And those units are kilograms times meters per second squared, which are the same as newtons. Now, the meaning of kinetic energy. There are a lot of ways to talk about the meaning of kinetic energy. The way that I've chosen to talk about it here is that the kinetic energy is the work required when we accelerate a mass from one velocity to another. The change in kinetic energy would be the work required. The kinetic energy itself is the work required if we accelerate the mass from rest to some velocity. When an object is at rest, we say it has zero kinetic energy. When we've accelerated it to velocity, some final velocity, then we say it does have kinetic energy, and that kinetic energy is equal to the work we had to do by the net force to accelerate it. If there's some friction, then we have to exert a little more force, so we might do more work than the net force does. The net force would, of course, be our force minus the frictional force. we note that kinetic energy can then be converted into potential energy or work. Most notably, if we've accelerated an object along some surface where there's some friction, and we attain this kinetic energy, we can release the object, take our force away from the object, and friction will stop the object. The object will have to do work against friction. So it's converting its kinetic energy into work. Or if we give an object enough velocity in the upward direction, any velocity in the upward direction, and release it, of course the kinetic energy can convert to potential. And we've been through the details of these processes many times. This is a very important concept. An example here is the example of a 2 kilogram mass moving at 5 meters per second, then its kinetic energy is 1/2 mv squared, because that's the work we get if we accelerate a mass from v0 to vf with some net force. Doesn't matter what the net force is, that's the way it's going to work out. It's always going to be 1/2 mv squared. And that's a straightforward calculation. The units are kilograms times the square of velocity units, kilogram meters squared per second squared, which is, of course, I've got kilogram meters per second times meters. I took the square off my meters and took it off my seconds also. That should be kilogram meters per second squared times meters. And this is, of course, Newton, so that's Newton times meters or joules. Quickly looking at the concept of work. Work is the force, or the component of the force that's parallel to the direction of motion, times our displacement. For example, a 200 Newton force implicitly in the direction of motion for a 100-meter distance gives us a work contribution of 20,000 joules. Units are force times distance, Newton meters, which is joules, and as we saw before, that's the same as kilogram meters squared per second squared.